These are P3 revision questions. I've got a couple of highlighters and a calculator so that I'm ready to go. So energy resources can be renewable or non-renewable. Coal is a non-renewable energy resource. Name two other non-renewable energy resources. We could have oil, we could have natural gas, or we could have nuclear. So remember that nuclear is non-renewable, but it's also not a fossil fuel, whereas coal, oil and natural gas are fossil fuels. Wind turbines are used to generate electricity. The graph below shows how the power output of the wind turbine changes over one day. So time in hours on the x-axis, power output in megawatts on the y. A wind turbine does not generate electricity constantly. For how many hours did the wind turbine generate no electricity? So we're looking for when the power output is 0, and that starts here and ends here. So we need to read off our axis. So this would be 12, 14, 16, 18, 20. So between 14 and 18. So we want to find the difference between those, and that's 4 hours. So next question accidentally was over 2 pages. Sorry, this wouldn't happen in an exam. So we have electrical power is transferred from power stations to the national grid. What is the national grid? So we've got some tick boxes here. A system of cables and pylons, a system of cables and transformers, a system of cables, transformers and power stations. It's cables and transformers that are the things that are in the national grid. Power stations are not considered part of the national grid because it's from power stations to the national grid. An island has a large number of wind turbines and a coal-fired power station. The island needs to use the electricity generated by the coal-fired power station at certain times. Choose one reason why. So why does it need to use the coal-fired power station sometimes? Tick one box. Wind is a renewable energy resource. Wind turbine power output is constant. Power output of wind turbines is unpredictable. The fuel cost for wind turbines is very high. So this is what's called a distractor. Wind is a renewable energy resource because that's true. It's a true statement, but it doesn't explain why we need to use coal sometimes. So that's trying to distract you, because sometimes you might read that and think, oh, that's correct. Well, it's a correct statement, but it's not the reason why they need to use coal. Wind turbine power isn't constant, and we can see that from the graph that we've just used. And there isn't a fuel cost for wind, so therefore we can see that it's because the power output is unpredictable. You might have got to that straight away, but it's always useful looking at strategies of how to approach multiple choice questions. A wind turbine has an average power output of 0.60 megawatts. A coal-fired power station has a continuous power output of 1,500 megawatts. Calculate how many wind turbines would be needed to generate the same power as one coal-fired power station. So we have 1,500 megawatts. So 1 megawatt is 1,000,000 watts. So if we were doing a calculation where one was in watts and one was in megawatts, we would need to convert them both into watts. But because we're looking at because it's a consistent unit for this, we don't need to convert anything. So basically we want to know how many times 0.60 goes into 1,500. So we just do 1,500 divided by 0.60. Oops. So we would need 2,500 wind turbines to replace the coal-fired power station. So it is important that scientists develop new energy resources. Choose one reason why. So all energy resources are running out. All energy resources are used to generate electricity. Most energy resources have negative environmental effects, and it's that bottom one there. Not all energy resources are running out. Renewable energy resources aren't running out by the very definition of what they are. Not all energy resources are used to generate electricity. Remember that some are used for heating, some are used for transport. but all of them have some sort of negative environmental effect. So question 2, this would be common to the higher paper and the foundation paper. Question 1 was just the foundation paper. A farmer has installed a biogas electricity generator on his farm. This device generates electricity by burning the methane gas produced from rotting animal waste on his farm. Methane is a greenhouse gas. When methane burns, carbon dioxide and water are produced. The animal waste rots in an anaerobic digester. The digester and the generator are kept inside a farm building and cannot be seen from the outside. The animal waste used in the anaerobic digester is a renewable energy source. What is meant by an energy source being renewable? So we've already kind of mentioned it so far, but either we can say it will not run out, or in this case, it will be replaced very quickly. Okay, so he's going to use the animal waste is going to rot down and produce methane, which he then uses, but it's going to be replaced a lot of the time because, or very quickly, because it's a farm, so there's lots of animal waste. Suggest one reason why farmers have been encouraged to install their own biogas generators. There's lots of different reasons that you could say for this. So we could say that it reduces the demand on the national grid or on fossil fuel power stations. That's absolutely fine. You could say about the fact that because they have lots of the waste or the fuel available. Okay, so mentioning what I've just said a few minutes ago, you could say about the fact that it will save them money, or they could sell back to the national grid. So lots of different reasons that you could get for this. So the farmer's monthly electricity bill using the mains electricity supply was £300. The biogas generator cost the farmer £18,000 to buy and install. Assuming the biogas generator provides all the farmer's electricity, what is the payback time for the generator? So how long does it take for them to pay back this £18,000? So it costs them £18,000, but every year they then don't have to pay the £300 for the mains electricity supply because all of their electricity is supplied by this. So we just need to do 18,000 divided by 300 because that's their monthly supply. So how many months that would be. So 18,000 divided by 300 would take 60 months. It doesn't tell you to put it in any particular unit, so you could leave it in months, but if we wanted to, we could divide by 12 to save 5 years. Okay, it would have been cheaper for the farmer to have bought and installed a small wind turbine. Give 2 advantages of using the biogas generator rather than a wind turbine. Okay, that bit is really, really important. Okay, it's not just asking for advantages of a biogas generator, it's asking for advantages of a biogas generator rather than a wind turbine. So the first thing that a lot of people write when they want to talk about something that's renewable is they would write it's a renewable energy resource, but it's asking you to give advantages of this over wind, which is also renewable. So it being renewable isn't enough because both of them are renewable energy resources. Okay, the most obvious one I think is that it is reliable, so it doesn't depend on the weather. Okay, if it's not windy, then then you're not going to get very much power being generated by the wind turbine. You could say either of these things and you would get the mark. You could also say about the fact that it uses waste products. So these waste products just would have been wasted before. So therefore, you might as well be using something. The other thing as well was they gave you a hint in the first bit of the question. The digester and the generator are kept inside the farm building and cannot be seen from the outside. So this is one of those things that people who don't like wind turbines always go on about. So you could say no visual pollution is the phrase that they use. So people call it visual pollution when you can see a wind turbine and it disrupts the landscape, so you can't see it. So question 3 is higher paper only. So if you're doing the foundation paper, you could have a go at this, but it's more advanced than a question that you would expect to see on your paper. So you could stop the video here if you're only doing the foundation paper. The image below shows a solar thermal power station that has been built in a hot desert. This power station uses energy from the sun to heat water to generate electricity. Energy from the sun is reflected towards a solar receiver using many mirrors. So you have a diagram. It shows you that the solar receiver is this part here, and these are all the mirrors that are pointing up towards the solar receiver. So which part of the electromagnetic spectrum provides most of the energy to heat the water in a solar thermal power station? Is infrared radiation. The clue is the thermal part. We will do more about infrared radiation when we do the electromagnetic spectrum later on in paper 2. But you came across this in year 8 anyway, so you are already familiar with infrared radiation. Describe how heated water is used to generate electricity by this solar thermal power station. The process is the same as in a fossil fuel power station. So how do we use heated water to generate electricity? So it's a 3-mark question. So the water is heated to make steam. The steam turns a turbine. The turbine spins a generator. And the generator generates electricity. It's these 3 steps, and they're going to be the same in fossil fuel power stations, in nuclear power stations, in this kind of solar thermal power stations. Always we're heating water, geothermal power stations as well. Water being heated to make steam, steam turning a turbine, turbine spinning a generator. Even this part, turning a turbine, turbine spinning in a generator, is how the vast majority of electricity is generated. Even like wind, wave, everything. So this kind of phrase of something turns a turbine, the turbine spins a generator, is something that is really helpful for you to learn. That kind of wording helps to describe it really easily. Okay, a new type of solar power station called a solar storage power station is able to store energy from the sun by heating molten chemical salts. The stored energy can be used to generate electricity at night. It is important that the molten chemical salts have a high specific heat capacity. Suggest one reason why. So specific heat capacity is from P2, and that's the energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So therefore, if it has a high specific heat capacity, then large amounts of energy can be stored. So the solar power station can store a maximum of 2,200,000 kilowatt hours of energy. The solar power station can supply a town with a maximum electrical power of 140,000 kilowatts. Calculate for how many hours The energy stored by the solar storage power station can supply the town with electrical power. Give your answer to 2 significant figures. So it's a 3-mark question. Okay, so let's remember that kilowatt hours is a measurement of energy. I mean, it does say of energy, but let's just remember that. And we have a power here, and we're being asked to find a time. So first of all, we need the equation that links these 3 things together, which is energy equals power times time. You need to make sure, so we're being asked, so we've got an energy in kilowatt hours, and we've got a power in kilowatts, so our time will be in hours. The other unit for energy is the joule, and if it's joules, you need to make sure that you're using watts and seconds as well. So we've got our equation, energy equals power times time. We're going to substitute in our values, and then we're going to rearrange. So energy equals power times time. Our energy is 2,200,000. Our power is 140,000. And our time is what we want to find out. So at the moment, I've got time multiplied by 140,000, so I need to do the opposite of multiplied by 140,000, and I need to divide by 140,000. Whatever I do to this side, I need to make sure I do to this side as well. I'm just going to write it underneath here. Which will give me the time, which will be 15.71428 and some stuff. And it's asked me to give it to 2 significant figures. So I count 1, 2, and so I would want to cut it off here. And then I look to this number, so because it's 0.7, 7 rounds up, so therefore 16 hours is the time that I can do it for. Okay. Table 1 gives information about where the solar power station has been built. So we have the season, spring, summer, autumn, winter, the mean number of daylight hours here, and then the mean power received from the sun per square metre in kilowatts. The solar storage power station does not operate at the maximum possible electrical output every day of the year. Suggest why. So the solar is linked to the number of daylight hours, so it's not going to be maximum because I can see that the daylight hours varies. Sorry, let's be specific. Number of daylight hours varies depending on season. But this is a 2-mark question, so that's not going to be enough. So the number of daylight hours varies depending on the season, so the mean power received also varies. So power stations do not work at a maximum possible electrical output all the time. The capacity factor of a power station is calculated using the equation. Capacity factor equals actual electrical output per year divided by maximum possible electrical output per year. Table 2 shows capacity factors for different types of power station. So we have coal, natural gas, nuclear, solar thermal, tidal, wind turbine. Says whether they're renewable or not, and then says their capacity factor. Compare the capacity factors for the renewable power stations with those of the non-renewable power stations. Explain the reason for the difference between these capacity factors. So let's have a look. This is worth 3 marks. We want to see both of these sheets at the same time. So first thing that you might think is you might panic because you haven't ever seen this equation before, but you don't need to have seen this equation before necessarily. Sometimes they will throw stuff at you, which is just new information. So that it's usually called a novel question or a novel scenario. So it's something that you haven't seen before, but it's whether or not you can apply what you know about physics or whatever to the situation. Okay, so you're not actually expected to do anything with this equation necessarily. What they're doing is they're trying to explain to you what this column actually means. So what we want to do is compare renewables and non-renewables in terms of their capacity factor. So we're basically comparing the first half of the table with the second half. So I would find it helpful to draw a line like this so that my eyes find it easier to chunk it up in that kind of way. Otherwise, I think sometimes tables can feel quite overwhelming, and then I think it's easier for you to kind of compare these capacity factors. So straight away, I would expect that you can see that non-renewable energy resources or non-renewable power stations have higher capacity factors. Okay, so that's the first statement. That's going to get you a mark. Okay, and that's comparing. So now we need to think about explaining the reason for the difference. So a reason for the difference is that, as you saw in the previous question, this one where it said about it doesn't operate at the maximum electrical output, and we said that was because the number of daylight hours varied throughout the year, that all of these solar and wind are dependent on weather. Tidal isn't dependent on the weather because it's dependent on the moon, but it does only happen at certain times of the day. So renewables tend to depend on the weather. So they're less reliable. And you could then say about the fact that the fuel for these is always available. So you're basically saying the opposite of this statement. So non-renewables, fuel is always available. So you could have a fossil fuel power station going the whole time because the fuel is always available. And then the last question, the capacity factor of a solar storage power station is higher than for all other renewable power stations. Suggest reason why. So suggest one reason why it might be higher for all of the renewable power stations. So this, we really want to link it to, again, they've given you kind of a clue with this. So it can generate electricity for more hours. Okay, so therefore there'll be more daylight hours and there will be hours where the tide is coming in or out, or hours where it's windy, or hours where the waves are big enough to be generating as much electricity as they can.